Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industrial and System Engineering. This lecture is on multivariate time series. Up to this lecture, we've learned how to model univariate time series in the sense that we would model and forecast the time series based on only the past values of the time series, disregarding the impact of other factors or other time series on the forecasting and the prediction of the time series. In this lesson, and starting with this lesson, I will introduce a class of models for multivariate time series. What is a univariate time series? A univariate time series is a sequence of random variables with some similarity in terms of the probability distribution called a stochastic process. For a time series, the sequence of random variables is indexed by time. In previous lectures, again, I introduced statistical properties of such univariate time series. We can expand the concept of univariate time series to multivariate time series, which means that instead of having one time series, we have a collection of n time series, possibly related or correlated in time. Throughout this lecture, we will use multiple notation to refer to a multivariate time series. We can write it as boldface y, which is the collection of all n time series together, but we also can refer to as yt, which is the collection of the time series data at time t only. Note that here yt is a vector of n variables, each being the time series value of one of the n time series. Why do we need to model multivariate time series? Multivariate time series analysis is used when one wants to model and explain the interactions and co-movements among a group of time series variables. It is possible to improve the prediction of one time series by taking into account other factors, as I will illustrate with 3 examples in this lesson. Simply taking into account the historical data of the time series itself may not provide as good predictions as when we also account for historical data of other factors. Generally, multivariate time series has been applied in econometrics and financial data. Examples are in simultaneous modeling of forward and spot exchange rates, or interest rates, money growth, income inflation, or consumption and income. But as I'll illustrate in this lecture, there are many possible applications in other fields, for example, in environmetrics, climatology, among others. I'll begin illustrating the concept of multivariate time series using a classic econometrics example, the relationship between interest rates and unemployment, a topic of interest in the past 2 years in the United States, as the Federal Reserve, or commonly referred to as the Fed, had started to slowly increase the interest rate. The Fed meets 8 times each year to review economic and financial conditions and decide on monetary policies. Monetary policy refers to the actions taken that affect the availability and cost of money and credit. At these meetings, short-term interest rate targets are determined. Before starting the increase of the interest rates, the Fed had established that it will start increasing the interest rates if the unemployment gets below a specific threshold value. But what is the relationship between interest rates and unemployment? There's a more direct correlation than most people understand. The relationship is driven by the so-called wage pressure. When you hear the Fed saying that the economy is heating up, we have to raise interest, what they really mean is labor is asking for and getting higher wages. We cannot have that. Let's make it harder to get money. Thus, we should expect that the interest rate is more accurately predicted if we take into account not only historical data for the interest rates, but also the unemployment rate. To do so, we will need to employ multivariate time series modeling. These are the time series of the interest and unemployment rates observed monthly. We see that over the period of 60 plus years, there were periods of time where the two series show similar patterns. However, in the past years, since around 2009, the rates were zero, while the unemployment went up and then down. Thus, unemployment rate indeed leads to changes in the interest rate. After how many lags in month does the interest rate respond to the reduction in the unemployment rate? We'll address this question in this lecture. For the second example, we'll return to the case study forecasting the Alaskan moose population. This case study was used to illustrate the application of the ARIMA model in the previous lecture. The population of wild moose in areas such as Alaska often fluctuates over several years due to both human influence and natural factors. The endpoint of this study is to predict the Alaska moose population. In this lecture, we will consider other factors which may impact the rise or fall of the moose population. Why is it important to predict the Alaska moose population? For many Alaskans, moose meat is the largest source of food income for a family. Thus, it is of great importance to the Alaskan citizens to manage and control the moose population to ensure the sustainability of this population. Moose also serve as an important tourist attraction which helps to bring several thousand people to this great state every summer. The findings established in such a study can be of particular use to Alaska Division of Wildlife Conservation, which tracks populations of species across several years for scientific and conservation purposes. The data provide relevant factors related to moose population, including population of Fairbanks, which is close to the location Unit 20A, for which we have the data on moose population, Alaska wolf population, average snowfall, and moose harvested. The years of the data are 1965 to 2006, and the data are yearly. The data come from multiple sources, but are particularly acknowledged the Alaska Department of Fish and Game. The time series plot of the factors in this data sets are here. We'll focus on the total moose population in the study. We can see that many of the factors provided have some overlapping patterns with the time series of the total moose population. The question we'll address in this lecture is whether we can forecast the total moose population with the aid of other factors. Does the wolf population impact the moose population? Does the moose population tend to decrease with heavy snow? Again, such questions can be addressed with a multivariate time series analysis. From econometrics to animal wildlife population, now I will illustrate an application from environmetrics. We'll study the river flow of Chattahoochee. The Chattahoochee River originates in the Blue Ridge Mountain of Appalachian Highlands in northeast Georgia. The Upper Chattahoochee River watershed is the most important, if not unique, source of water supply for Atlanta. Thus, it is important to accurately predict the river flow or drainage. Our understanding of such environmental systems can be substantially improved by using multivariate time series analysis and modeling techniques. Two main time series, namely precipitation and ground air temperature, are used along with river drainage. The data are observed monthly over 60 years since 1956. These are the three time series. The first time series is the river drainage or flow. The time series presents some cyclical patterns, but there is not a clear trend over time. The next time series is for ground temperature. As expected, we see a clear seasonality. The third time series is for precipitation or rainfall. The seasonal variations in rainfall are not significant, even though there are visibly higher amounts of rain during winters. We expect a causal relationship of river flow with respect to this time series. During winter month, when the potential evapotranspiration is lowest in the year, the stream flows are mainly determined by the precipitation. While during summer month, when the potential evapotranspiration is higher than the amount of water falling within the watershed, the stream flows are consistently low despite of the variations of precipitation. Thus, it is possible that the seasonality in rainfall and temperature to also improve the prediction accuracy of the river flow. how to deal with seasonality in the individual time series, especially when the seasonality in temperature and rainfall may impact the river flow. We'll address this again using multivariate time series modeling. And somewhere in this lesson, I introduced 3 examples that I will use to illustrate multivariate time series. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industrial and System Engineering. This lecture is multivariate time series, and in this lesson, I'll briefly introduce the concept of multivariate time series. To review, a multivariate time series is a collection of n time series possibly related or correlated in time. Throughout this lecture, we'll use multiple notation to refer to a multivariate time series. We can write it as bold-faced Y, which is a collection of all n time series together, but we also can refer to as YT, which is a collection of the time series data at time t only. Note that here YT is a vector of n variables, each being the time series variable of one of the n time series. Why do we want to model multivariate time series? Multivariate time series analysis is used when one wants to model and explain the interactions and co-movements among a group of time series. It is possible to improve the prediction of one time series by taking into account other factors, as I illustrated in the examples in the previous lesson. Simply taking into account the historical data of the time series itself may not provide as good predictions as when we would also account for the historical data of other factors. As we'll learn in this lesson, dependencies captured in multivariate time series are within and between time series. Thus, when forecasting one of the n time series, we take into account both types of dependencies. Similar to univariate time series, we also have the concept of stationarity in multivariate time series. A multivariate time series is stationary if the mean of each individual time series is constant over time, which means the expectation of the vector time series is a vector of means mu, not varying in time. Moreover, the variance-covariance matrix of the vector time series YT is a matrix defined here gamma 0, which does not depend on t, on time. Note that gamma 0, thus the covariance-variance matrix, measures the so-called contemporaneous dependence in the multivariate time series. I'll introduce the covariance matrix for lag dependence on a different slide in this lesson. Furthermore, we can define the contemporaneous correlation by R0 by scaling by the standard deviations of individual time series in the vector time series as provided on the slide. D0 here is a diagonal matrix where the ith element on the diagonal corresponds to the standard deviation of the ith time series. We can estimate the mean contemporaneous variance covariance and correlation for a multivariate time series using the sample data. For the mean vector, we estimate each mean in the vector by the average of the time series corresponding to the mean. For the variance covariance matrix, for the contemporaneous variance covariance matrix, we can use a sample covariance estimator as provided on a slide. In univariate stationary time series, we define the lag dependence using the autocovariance or autocorrelation functions. For stationary multivariate time series, we have the autocovariance or correlation for individual time series, but we also have the so-called cross-lead lag covariances and correlations between all possible pairs of time series. How are these defined? Consider a pair of time series from the multivariate time series with index I and j. The lead lag covariance for this pair is defined here on the slide by gamma ij for lag k, which is the covariance between the ith time series at time t and jth time series at time t minus k. The lead lag correlation is simply the scale lead lag covariance. It's important to remember that the lead-lag covariances and correlations are not symmetric. For example, gamma ij at lag k is not equal to gamma ji at lag k. This means that the dependence between the time series I at time t and time series j at time t minus k is different from the dependence between the time series I at time t minus k and time series j at time t. The lead-lag covariance capture the lead and lag relationships between time series in the multivariate time series. Yjt is said to lead Yit if the covariance between y at time t and yj at time t minus k is different from 0. It is possible that yt leads yjt and vice versa. In this case, we say that there is feedback between the two time series. Similar to the contemporaneous covariance and correlation, we can estimate the cross-covariance and cross-correlation using the sample data. Instead of estimating based on the contemporaneous products of pairs of time series, now we use the lead-lag products of pairs of time series. That is, take the sum of the products between yt and yt minus k. Again, note that the matrices gamma k and rk will not be symmetric. I'll illustrate this with an example in the next lesson. In summary, in this lesson, I introduced the concept of autocovariance and cross-covariance for multivariate time series. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industrial System Engineering. This lecture is on multivariate time series. And in this lesson, I will illustrate the concept of autocovariance and cross-covariance functions for multivariate time series using a data example. Specifically, I will illustrate the estimation of the dependence of multivariate time series using the data example in which we're interested in capturing the relationship between interest rate and unemployment rate. The two time series are in two different data files with different structures, as you will see when you'll open the files. The interest rate is read from interest_rates.csv file, which consists of two columns, one for the date and one for the interest rate value. Thus, we can directly read the data column with the interest rate into a time series. The data file for unemployment is in form of a matrix where each row corresponds to a year and each column corresponds to a month. Thus, we'll convert the matrix of unemployment data values by using as-vector command, which stacks the columns of a matrix into one vector. Since we want to stack the rows to keep the time order of the data, we first take the transpose of the matrix and then apply the as-vector command. We discard the first column of the data since it provides information on the years. After this data processing step, we can convert the vector of unemployment rates into a time series. To combine the two time series into a multivariate time series, we can use the TS_R command. This step is needed in estimating the autocorrelation and cross-correlation using the ACFR command. The correlation plots are here. On the diagonal, we have the autocorrelation plots for the two time series. Off diagonal, we have the cross-correlation plots. The autocorrelation plots indicate that neither of the two time series are stationary since the autocorrelation decreases slowly with the increase in the lag. The cross-correlation plots are different. Recall that in the previous lesson, I mentioned that the lead-lag correlation between any pair of time series is not symmetric. That is, it depends on which time series is in the pair as the lead and which one is the lag time series. In these plots, the first time series in the title of the sample cross-correlation plots is the lag time series. For example, in a cross-correlation plot in the lower left panel, the interest rate is the lead and the unemployment is the lag time series. That is, this plot presents the estimated cross-correlation for interest rate at time t minus k and the unemployment at time t.
Note that the lags are provided in reverse order. The last bar in this plot corresponds to the contemporaneous correlation, that is the correlation of interest rate and unemployment rate, both at the same time t. The next to the last bar corresponds to the correlation between interest rate at time t minus 1 and unemployment at time t, and so on. How can we interpret the lead-lag correlation from this plot? The contemporaneous correlation is very small, but there is a lead-lag relationship as the cross-correlation values are large. In fact, very slowly increasing as the lag increases, which is an indication that unemployment indeed lags interest rate, but over a long period of time. In contrast, if we look at the estimated cross-correlation, where the unemployment is the lead time series, we see that the cross-correlation is small, suggesting that unemployment rate does not lead the interest rate, which is counter the argument of the economic theory of setting interest rate based on the level of unemployment. If we would like to get the correlation values, we can use the core command in R. For example, the contemporaneous correlation is 0.16, while the lead-lag correlations within one lag are 0.17 and 0.15. However, our interpretation of the cross-correlations from the previous slide is for non-stationary time series. It is more appropriate to provide such interpretations for stationary time series. For this, we can take the first order difference of the two time series and assess the relationship between the differences in the two time series. That is, does the difference in unemployment rate impact the difference in the interest rate from one month to another? These are the autocorrelation and cross-correlation plots for the difference time series. The autocorrelation plots show that the first order difference improves the stationarity of the two time series. The autocorrelation does not show a slow decrease over many lags. The cross-correlation plots provide a different interpretation than in a previous slide. The cross-correlation plot with unemployment as the lag time series and interest rate as the lead time series in the lower left plot. The correlation estimates are small, suggesting plausibly no lead relationship of the change in the interest rate to the change in unemployment rate. However, from the cross-correlation plot in the upper right plot, we see that there may be a lead relationship of the change in unemployment rate versus the change in interest rate, which aligns with the economic theory. We can compare the lead-lag correlation using the two time series and the difference time series. We can see that the cross-correlation increases for the difference time series. In the next two examples, I simulate multivariate time series when we know how the autocorrelation and cross-correlation plots need to look like for a better understanding of the interpretation of the plots. First, I simulated white noise, which will be the first time series, where the second time series is the same simulated white noise but lagged with 3 lags. We'll look at the autocorrelation and cross-correlation plots. These are the plots. As expected, the autocorrelation plots indicate that the time series are white noise. For the cross-correlation plots, only the one for which the time series E2 is the lead and the second time series the first time series E1 is the lag time series, showing one large correlation value at lag 3. This means that there is a large correlation between E1 at t and E2 at t minus 3 from our simulation. The t minus 3 E2 is exactly the E1 at time t, and hence the large correlation at lag 3. In contrast, the other cross-correlation plot has no large correlation, no large values. This is because E1 and E2 are white noise processes. Next, I will provide a simulation example in which we simulate two correlated AR time series. The first time series of white noise, whereas the second is an AR1 process and a lead process for the first time series with 2 lead lags. Next, I will provide a simulation example in which we simulate two correlated AR time series. The first time series of white noise, whereas the second is an AR1 process and a lead process for the first time series with 2 lead lags. The R code for the simulation is here. First simulate the white noise time series defined by X, and the white noise for the second time series defined by E, the vector E. To simulate the second time series Y, we loop over all k in 1 to 500, and for each index k, the time series Y is defined as an equation above, with the coefficient 0.8 for the yt minus 1, plus the white noise E, plus the coefficient 0.6 times xt minus 1, and the coefficient 0.3 times xt minus 2. The ACF plots of this multivariate time series are here. The autocorrelation of X indicates white noise, while of Y clearly shows that there is autocorrelation. In order to detect the order of AR for Y, we would need to look at the PACF plot. The cross-correlation plots show that X leads Y, but Y does not lead X, as we see that the cross-correlation for lags 1, 2, 3 are outside of the confidence band. Indeed, from our simulation model, X lags Y with 2 lags, since Y is a function of xt minus 1 and xt minus 2.
In summary, in this lesson, I illustrated the lead-lag relationships between Y time series with simulated examples. Thank you.